Okay, in this video here, we're going to solve the first problem that was due for homework in the Chapter 10 or the refrigeration chapter. This particular problem calls out a large refrigeration plant that is to be maintained at minus 18 degrees Celsius, and it's required refrigeration at a certain rate of 200 kilowatts. Again, that is the heat transfer that is going to be taken away from the from the area maintained at this lower temperature. The condenser of the plant is to be cooled by liquid water, which experiences a temperature rise of 8 degrees as it flows over the coils in the condenser. The coils themselves hold the refrigerant. Assuming that the plant operates on an ideal vapor compression cycle using refrigerant R134A as the working fluid, between the pressure limits of 120 and 700 kPa, we want to determine the mass flow rate of the refrigerant, the power input to the compressor, and the mass flow rate of the cooling water. And so in this particular case, we're going to set up our four states again. We're going to observe that this particular lower pressure, when we look at the temperature associated with the R134A at this pressure, we want to make sure that it is lower than the minus 18 degrees Celsius for there to be heat transfer. We're going to start the problem by, first of all, running 1 kilogram per second through the system and seeing what the refrigeration rate is and compare it to 200 kilowatts, and then we'll augment or we'll proportionally increase or decrease the flow rate in order to obtain that value. After doing that, then we're going to look at the condenser side and we're going to say, okay, how much water, how much cooling water has to flow through wherein only it rises only 8 degrees of temperature as it takes on or takes the rejected heat out of the system. And we'll come up with that particular flow rate as associated with the cooling water. But the first thing we're going to do is we're going to figure out the mass flow rate of the refrigerant that we need and its corresponding power input. And so with that in mind, we're going to go to our test app. We're going to go to our vapor compression gas refrigeration cycle. Our fluid, our refrigerant, is a phase change refrigerant, and we then go to the HTML app. This doesn't involve any exergy, and so we're able to dispense from setting up the dead state. What we do know is that going into the compressor, coming out of the evaporator, is a pressure of 120 kPa, and our quality is 1. And so at this particular condition, what I forgot to do is I forgot to select the proper working fluid, which is refrigerant, and it's 134A. And so upon putting in the pressure and the quality and doing a calculation, we see that yes, indeed, the temperature of the refrigerant is at a low enough temperature in order to absorb any of the heat from the minus 18 degree cold region. I'm going to set up my m dot equal to 1, and now we're ready to move on to our other conditions. This is an idealized system, and so being that it's an idealized system, the output of our compressor will be at the 700 kPa that was designated in the problem. The entropy will be unchanging. It will be equal to S1. And again, the m dot we'll designate as m dot 1. And so now we have the output of the compressor is at a temperature of 34.33. And so now we're ready to go through the process of condensation, de-superheating, and then followed by condensation at that same pressure, pressure 2. We're going down to the idealized saturated liquid condition at an m dot equal to m dot 1. And we see that the temperature is 26.65. And so what this tells us is that whatever we use for our cooling water, the final temperature is 26.65. And so if we're trying to reject heat, we have to make sure that even after the increase in 8 degrees, that our cooling water stays at a lower temperature than the lowest temperature of our refrigerant. So we're going to go ahead and we're going to say that our cooling water comes in, let's say at 15 degrees Celsius. Now we could actually come in a little bit higher. If we are using a counterflow heat exchanger, we can have a portion of the heat exchanger wherein we have a certain temperatures. We can actually allow the highest temperature, which is after it absorbs and goes to at least 8 degrees above. We could have that at the portion associated with the incoming refrigerant where it is the highest. But we'll go ahead with 15 and make sure that it doesn't get any higher than 23. And then finally we have our last state, which is going back to state 1. This is our expansion valve, and we have the enthalpy given as well as the m dot. Okay, so now that we have all of our states, we then can go in, for right now, we can go in the device panel and put in the devices of interest. And the first device will be the compressor, and it goes from 1 to 2 with no heat transfer. And so with a mass flow rate of 1 kilogram per second, we see that the work input is 36.6. Okay, we can then go to our condenser. Now, our condenser is going to be a non-mixing two fluids type of condenser. But for right now, I'm going to treat it as just a single one from 2 to 3. And this would be the condenser with no work being done. And we see that it has to reject heat at this particular rate. Okay. A little bit later, when we add the cooling, we will add the cooling and put in another line with water instead of the refrigerant, and we'll set this equal to 0 in order to set this equal to 0 to determine the mass flow rate of the cooling water once we get the mass flow rate of the refrigerant set. And so then finally our device 3 is going to be our expansion valve, which we really don't need to do it, but we can go ahead and put it in. It's constant enthalpy, so the heat transfer and the work are equal to 0. And then finally our last state, or last device panel, is the evaporator, where the cooling effect is actually occurring, and we know that there's no work there. And what this tells us is that for a flow rate of 1 kilogram per second, we get a heat transfer rate of 147.44. And so I'm going to, for whatever reason, it doesn't allow me to copy and paste that number, so I'm going to write that number down. And so now I'm ready to do a super calculate. And upon doing the super calculate, I have all of the various conditions. I'm going to go back to the state panel, and now I'm going to augment or modify this mass flow rate. And this mass flow rate is going to now, instead of being 1, it's going to be equal to the amount that we want the heat transfer to be divided by that 147.557. And so again, over the period of this course, we've done that enough times, scaling everything in order to get the correct mass flow rate. If we were to super calculate and go back to the state panel, we would see that that's shows up here, and each of these M dots will be the correct M dot. Now, if we were to go back to the device panel, we would then see that here's a work of our compressor. It goes up to 4965. That's actually one of the questions that's asked, is the power input of the compressor. So 49.65 kilowatts at the new flow rate. And then we go to our okay, something happened here that did not, this should have come back at 200 kilowatts. Again, if we did the mass flow correctly. So what I'm going to do is I'm going to go back to my state panel. I'm going to go back to 200, okay, divided by that. I'm going to go back and put this in as 1, and I'm going to recheck this. And so I'm going to super calculate, and then I'm going to go back to my device panels, and I'm going to see that here is my work of the compressor. And then I'm going to see that this is the heat transfer away from the condenser. And so that's different than what we had before. And so something is amiss, and so I'm going to write that down. And then here is our expansion valve, and then this is, okay, I'm sorry, it is 147.557. So this is the refrigeration that's occurring. And so what I failed to do here is I looked at the condenser and not the evaporator to check to see if it went to 200. And so I'm going to go back, I'm going to do a super calculate, I'm going to go back to my state panel, and I'm going to bring this back to what it was. And it was 200 divided by 147.557. Hit return, do a super calculate, and then go back to my devices. And now if I look at my devices, here's my compressor work, same as we talked about before. This is the condensation heat transfer. This is what the cooling water is going to take away. And then we have nothing happened in the expansion valve, and now we're back to 200 as our heat going into the evaporator. And so this is the refrigeration capacity that we are attempting to do. And so we now have it set up. We have figured out what the flow rate of the cooling water should be. And now we're ready. Well, we figured out what the flow rate of the refrigerant should be. If we wanted to go back to the I/O panel, we can put in and say, go ahead and print out for us the M.1. And we see that the answer is 1.355. And so now we're ready to go and try to figure out what is the flow rate of the cooling water. So we go back and we say, okay, the cooling water is going to be two states, the incoming state and the outgoing state. Now, we can switch fluids here, and we're going to go ahead and switch fluids to either water or compressed liquid water, which we know that it is in the compressed liquid condition. And so here then is our water, our incoming water, and we're going to say that our incoming water, we're going to give it, we'll give it a pressure, let's say, of 1 atmosphere. And we'll go ahead and, as we said before, we'll make the temperature of the water equal to 15 degrees Celsius. Okay, now we're not going to put an M.5. We're going to allow it to calculate M.5. And so now we're ready to move over to the outlet condition. and we're going to say that the outlet condition, again, of the water is going to be 8 degrees higher than the incoming. And so it's going to be, instead of 15, it's going to be 23. And again, now here's where we put m.5. And so it does not show up as being calculated because it still needs to be calculated. Now we can go and we can go to our device panel and we can, this is our refrigeration device panel. This here is our expansion valve. Okay, this right here was how we determined the original heat release that had to occur. And this is the one that we can change over, okay? But what I'm going to do, and this is allowed, I'm going to go to a fifth device. And as long as this fifth device does not have any work or heat transfer going into it, it's not going to affect the cycle conditions. And so I'm going to turn this fifth device into a multi-non-mixing device where I'm going to bring in the fluid, the refrigerant from the compressor through to the output of the condenser. And the other fluid that I'm going to put through is the water, which is state 5 to state 6. Now for this device, we're going to say that there's no work and there's no heat transfer. And so what this is going to then do is it's going to take the m dot of the refrigerant times the delta H, and it's then going to compare that to the m dot of the water times its delta H. And it's going to set those equal to each other, and that's going to determine for us the mass flow rate of the water, of the cooling water. And again, because there's no heat transfer or work, it's not going to show up in the cycle panel affecting anything that we may want to see in the cycle panel for the overall cycle. It's all internal. So we're going to do a super calculate. We're then going to go back to the state panel, and we see that it then has calculated for us the value of the cooling water flow rate. And the cooling water flow rate then is 744. 744 for 5 and 6. And again, we now have all the information that we needed. If we went to the cycle panel, we see here is the refrigeration effect. This is what is actually leaving the condenser through the cooling water. And then this is the net work that is occurring, 49 units coming in, nothing going out because the expansion valve doesn't do anything. And so the coefficient of performance for this system, if they had asked us for that, is simply going to be equal to this value divided by this value. And so you see that it's about a 4-to-1 coefficient of performance, 4.01. And again, because that extra device that we put in to get the cooling water flow rate does not have an impact on any of the heat transfers or any of the works, we then can determine the COP for the refrigeration cycle. We can go to the I/O panel to finish this up, and we can go and we can select and have it print out the m dot of 5, and we see that it's now 744.8. And again, we also in our output, if we are asked, it's not letting me go into my output here. Okay, I need to super calculate. And then once I super calculate, then I can scroll through my output and find the piece of information that we needed to put out, and that's this value right here. And so the net work, which is the work of the compressor, is 49.65 kilowatts. And so we have that, we have the two flow rates, and we're done with the problem. Okay, have a good day. Bye.